I think this may not be on. It's volume or differential control volume impacts the results of your governing equation. And as shown in this slide, from a fixed control volume reference frame, your finite control volume approach will basically give you a conservation, what we call conservation equations. Okay? What we call conservation equation. Whether you're going from integral to differential or differential to integral in both cases. Okay? On the other hand, for a moving finite or differential control volume, your equations result in what we call non-conservation forms. Okay, so here what I want you to pay attention to is the fact that what we mean by conservation, okay, and what we mean by non-conservation. Okay, and you see that once we talk about the derivations. As I pointed out earlier on, you would need a review of vector differential calculus. For example, what is a dot product and its derivative, what we mean by a cross product and its derivative, what we mean by a del operator, what we mean by the divergence of a vector field, the gradient of a scalar field, the divergence of a scalar multiple of a vector field, the dot triple product, the cross triple product, and the divergence theorem. These are all terminologies or vector differential calculus applications that would appear in the derivations that I'm going to discuss. I'm going to try and highlight some of them as we go along. Okay, so let us look at what we mean by a substantial derivative. On the left-hand side, that is this term, okay, we call that the substantial derivative, okay? And on the right-hand side here, we call that the first term, that is the quantity, the partial of the quantity Q with respect to T, we call that the local derivative. Okay, we call that the local derivative of the quantity with respect to time. And then these other partials times the velocities u, v, and W, we call those the convective terms. Okay? We can write this convective derivative term in a more compact form. That is this way. Okay? Using vector differential calculus, that is the dot product of the velocity, the dot product of the velocity and the del of the quantity q, of the scalar q. Okay? So what I'm saying is that the dot product of this velocity vector and the del of the scalar q basically is represented by the convective derivative. Okay? You can basically, why is that so? Well, note that the velocity is a vector quantity with terms u, v, and w, right? Orthogonal to each other, okay? And the quantity q is a function of x, y, z, and time. Okay, so when you perform, now the del of a quantity, okay, the del of a quantity is just the let me see if I can quickly represent it. The del of a quantity is just the partial of the quantity with respect to the x direction plus the partial of the quantity with respect to the y plus finally the partial of the quantity with respect to the z direction. Okay, and so basically you have this quantity q here, which is a function of x, y, z, and time, and so the del operator basically performs this operation. Any comments or questions? Note q can be density, velocity, in the x direction, velocity in the y direction, velocity in the z direction, or time. Any primitive variable is what we mean by the quantity q. Governing equations are usually expressed in terms of the substantial derivative, and so that is what you're going to see as we go on with this derivation. All right? Okay, and here, this is just showing that del.v just gives you, since v is your vector, then that means that you'll be taking the partial of the three terms of the velocity vector, okay, in rectangular coordinates. Now, in fluid dynamics, this is defined as the time rate of change of volume of a moving fluid element per unit volume, okay? So this quantity in fluid dynamics means the time rate of change of volume of a moving fluid element per unit volume, okay? So it can also be represented by this substantial derivative of del, where del here is your control volume of a moving fluid element. Okay, giving you the divergence of a velocity vector. Okay, so let's look at the conservation of equations of fluid flow. Let us look first at deriving the conservation of the continuity equation, basically the conservation of mass. And if I go back to this cube that I have drawn over here, I want to point out that, you know, I am in the figure that you see, let's say that we are only looking at this face here. Okay? We are just looking at this face here. However, you know, you have similar derivations that is going to be carried out for all the faces of this cube. Okay, we have similar derivations that is going to be carried out for all the faces of the cube. And so if we consider just the y and x plane, okay, if we consider the y and x plane, and so we are saying that into the board, okay, into the board will be the z direction, or out of the plane of the board will be your z direction, normal to it. Then, on this face, okay, on this face, the mass into the control, the differential volume is what? Mass is what? What is mass? How do we define mass? Density times volume, right? But density times volume can also be represented as velocity times area, right? Volume can be represented as velocity times area. That gives you your volume. So here we are saying that in the x direction, okay, in the x direction, you have the density times the velocity in the direction into the control volume times the what? Area. And what will be the area? the control volume. And so how is mass flowing in? Well, on this left-hand side, we have the density times the velocity times the area. The area will be the change in z direction times the change in y direction into in this space. And then out of the control volume, okay, would be the amount that may have entered, the amount that entered, plus a differential amount due to whatever changes is occurring within the control volume. Okay, we say that normally, this differential amount is what we call a Taylor series expansion, and we are dropping higher order terms. So we are just using a first order approximation to what this differential amount is coming out. Okay, so similarly, as we've looked on what is entering from this left-hand side of my cube to what is leaving from my right-hand side, I can also look at the top, from the bottom and the top, and also from face-wise into the board and out into the plane of the board. And so it gives rise to, from the bottom, well, you have the y velocity, which is density times the y velocity v times the differential area, and of course that would be delta x times delta z, and then out will be the amount that entered plus the differential amount that is leaving with the fluid. Okay. Similarly, for the case of the z direction, you have and let me write this down. For the z direction not shown, you have you have rho, you have the density times w, which will be the z velocity, plus the differential of the density times w divided by dz times delta z times delta x delta y. Okay, you see that on this next slide, that shows the differential amounts in all the three directions. Okay, in other words, the net flux into the system in the x direction would be just this term. Why? If we go back to this slide, well, from the x direction, this is entering, right? So that is your mass in, minus the mass out, so minus of this. So what happens? These two terms cancel each other, right? Okay, so you are just left with the negative of this term, okay? And so that's what you see here, okay? So the net mass flux in the system in the y direction will be similarly minus the partial of rho v dy times delta x, delta y, delta z. And then the net mass flux into the system in the z direction will be minus the partial of rho w dz dx delta x delta z. Okay? And of course, the rate of change of mass would be the density I'm going to pick on one of you if I don't have a volunteer. The ladies up front have been very quiet. So, you know, figure in a minute, figure it amongst yourself and tell us what would be the representation of the continuity equation for a constant density fluid. Okay, so let me help you. If we have a constant density fluid, what happens to the first term? It's zero, right? The derivative of a constant is zero, okay? And then what happens to these terms here? You can factor out the rho, okay? So it will just be rho times the del of the velocity vector. All right? Okay. Now, can we show that the continuity equation can also be written as in the non-conservation form? Yes, we can. Okay? You have to go back to the definition of the substantial derivative. Okay? That's your homework. Okay? And another homework, we've done this for rectangular coordinates. Now, we should be able to sit down and do it for cylindrical coordinate system. How about that? Okay? So, you have, they have my email address. Yeah, okay, we'll share it. I want that solution emailed to me. All right, so that's the continuity equation from the conservation of mass. Let us now move on to the momentum equation. As we stated in the beginning, the momentum equation is nothing but a statement of Newton's second law of motion that states that your acceleration, your mass times acceleration must equal the sum of all the forces that act on a given body. Okay? And those forces include surface forces as well as body forces. Okay? The body forces would be, for example, pressure, okay, would be electrical and magnetic field forces, okay. And then you also have gravitational forces also acting on the fluid, okay. So really, if we look at this sum of forces, for now, okay, since we are not going to do any complex derivations requiring that we consider electrical and magnetic field forces, we will say that for a given fluid element, the forces will be due to stress, and the stresses are the normal stresses, tau II, and the shear stresses, tau ij. Okay? And then it's also due to the pressure force and the body force. Okay, so these are the three forces that basically end up on the right-hand side of the equation. Okay, so let's look into expanding this. So note that the Newton's second law here, the left-hand side is written compactly in the form of a substantial derivative, okay? Let us have some understanding of what we mean by the components of these forces. What is the normal stress? Well, normal stresses tend to extend the fluid, okay? They tend to pull our normal to the face of the fluid and tend to extend it out. Those are normal forces, okay? Creating a strain in the fluid. On the other hand, the component tau ij are what we refer to as shearing components of the stress, which results in a shear deformation. That means that now, the shear forces, which is now acting perpendicular to the face, is causing the fluid to shear or to sort of slide layer by layer, starting from the bottom to the top, where the shearing force is maximum. Okay, for most fluids in contact with a surface, okay, we say that at the point of contact of the surface, there's what we call a no-slip condition. The force at the surface is zero. Because of no slip or no friction, the force is zero. So the force becomes more pronounced when you go up within the fluid and causes shear deformation. The pressure forces act normal to a surface and compresses the fluid particle. Okay, the pressure forces would compress the fluid particle. And then body forces basically acts in the direction of gravity. Okay? Any comments or questions? Now, let us look at a similar control volume for the momentum equation derivation. It's a very busy slide, and so let us try and see if we can identify the necessary forces on this differential fluid element. In the x direction, the stress times the area, of course, will give you force, right? Just like in the other directions. So now let us look at only the x direction, okay? You have tau xx, which will be the normal stress to the face, okay? Trying to extend the fluid, okay? So if I'm looking at the face 5, 6, 2, 1, I have this tau x delta y delta z, okay? Now, what would be, I want you to deduce the two other shear stress components on the face 5, 6, 2, 1. Okay, so that shear stress, okay, that shear stress acting on this plane, okay, acting on this plane will be acting parallel in the plane, okay, will be acting parallel in the plane. And let me try and draw it. Okay. So this is the tau x z. But you have to now multiply it by what area? What would be the area it's acting on? What is the area? It should be acting x, right? It would be your delta x times your delta z. Okay? So I'm just going to put it down here. It's difficult to delta x times okay, so that is the shear force acting in this plane. Okay, so similarly, you can come up with the shear stresses in other planes, and in each case, note that we find the normal stress. For example, here you also have to find the normal stress in the opposite side. So you have tau xx times the differential amount on the other side of the